Okay, this is the fourth video for the experimentation notes. In this last video, we're going to start by talking about how to analyze results. Data analysis and evaluation of evidence, we have to use this to help us to derive meaning out of nature. The purpose of science is to create and test models, and analyzing results is how we test models. So we gather information through measurements, calculations, graphing, and we now need to analyze it. And this can be the hardest part of any investigation, but it's essential because we need to answer experimental questions in order to be successful. So, interpreting data. Usually we begin by identifying what type of relationship exists between the independent and dependent variable. Linear, is it power, is it sinusoidal, is it inverse? What kind of relationship is it? Then we want to assess the accuracy and precision of our experiment. And remember that accuracy is found by calculating percent error, and precision is found by calculating standard deviation. Now we need to do an analysis of the uncertainty. So we need to talk about what causes uncertainty in a measurement. So first off, we have two types, systematic and random. So systematic uncertainties, and this is a longer definition. So these are uncertainties or error due to the calibration of an instrument. So did you fail to calibrate your triple beam balance? Are you using a meter stick that has a warped end to it? Something where the tool that you're using to make the measurement is not measuring correctly. That's a calibration error. These are also uncertainties due to faulty procedures or assumptions. So when you write out your lab procedure, are you doing something that would naturally lead to an error? Now, some examples of these would be parallax errors. Now, parallax is viewing something at two different angles. Whenever you read a meter stick or some sort of analog scale, you always want to view it straight on. You never want to view it at an angle. Now, we can't avoid parallax because if you think about it, we all have two eyes, so we are always viewing everything at two different angles. Next thing is the human reaction time. Human reaction time is right around 0.1 seconds. So we will always have that. And then there's air resistance. It doesn't fall within AP Physics 1 to calculate it, but it's something we want to take into account. When we work out models on the chalkboard or when we try to derive something, we often overlook air resistance, but in the laboratory setting, we really shouldn't overlook it. Now, when the systematic uncertainties in an experiment are small, the experiment is said to be accurate. And we talked about how a low accuracy is a low percent error. Okay, the next type are the random errors or random uncertainty. So, again, this is kind of a longer definition. Okay, these are random uncertainties, and really these are things that we can avoid. So, when you have an error in judgment in reading a meter, um, so if you look at a meter stick and you forget that the smallest line represents a millimeter, or when you're looking at a voltmeter and you don't realize that the smallest line is 0.25 volts, those are errors of judgment of readings of a meter. And you really, really should be able to avoid those. These are also uncertainties due to fluctuating experimental conditions. Remember that when heated, objects tend to expand, and when cooled, they tend to contract. Um, so again, these random uncertainties are really things that we should be able to avoid, because you want to know exactly how to read a meter, and you want to conduct your experiment under controlled conditions. Now, with that said, careful measurements of the same quantity by the same person will not yield the same results over multiple trials. It's just not going to happen. Um, and there are reasons for that. So again, experimental fluctuations, we want to be able to keep everything the same, but there's always going to be slight temperature variations. So, you know, things will expand with heat. Um, in electronics, uh, electrons will leak off of wires. So there's always a little bit of noise when you take an electronics measurement. And there's always small variations in start times. I mean, are you sure you started at 0 meters? Are you sure that the timer is turned on exactly at 0 meters? That's hard to do. Now, when the random uncertainty or random errors in the experiment are small, the experiment is said to be precise. So again, that's our standard deviation. Okay, so for AP Physics, here's some of the things you're going to be expected to do on the exams. You will not be expected to calculate standard deviations, use formal methods to calculate propagation of error, or carry out a calculated linear best fit. You're not going to be asked to do that. I can tell you in the lab setting, I'm going to ask you to calculate standard deviations, but not the rest. So some things that you will be able or should be able to do. You need to be able to discuss which measurement or variable in a procedure contributes most to the overall uncertainty. Is something giving you an uncertainty of 10% while something else is giving you an uncertainty of 1%? You need to be able to recognize that there may be no significant difference between two reported measurements if they differ by less than the smallest division on a scale. Um, So when we make measurements, if the change is so small between two measurements, we might as well call them the same. I want you to be able to reason in terms of percentage error, report results of calculations to an appropriate significant digit, uh, construct an estimated best fit line to data that you plot. So that's using a ruler and drawing your line of best fit. Articulate the effects of error and error propagation on conclusions drawn from a given data set. So you're looking at the error in your lab. Can you draw a reasonable conclusion? And then review and critique an experimental design or procedures and decide whether the conclusions can be justified based off of the procedure and the evidence presented. So basically critiquing someone else's experimental method. Okay, this wraps up our unit on experimentation. Ciao.